Hello, everyone. Welcome to a new session of the probability seminar. It is my great pleasure to introduce Gonzalo Contador, who is a mathematical engineer from Universidad de Chile, did his PhD at the University of Wisconsin, and now he's working at Universidad Técnico Federico Santa Maria. And today he's gonna talk about choosing between methods of combining discrete p-values. The floor is yours.
Thank you, Amitai. And thank you to the people of the probability seminar for the invitation. Hello, everyone online. Today I'm going to present an ongoing work with my colleagues Zheying Wen Hongxiang from WPI and the Broad Institute, respectively, on choices of methods for combining discrete p-values. The part that I forgot to highlight is that I'm not a PhD in mathematics, I'm a PhD in statistics.
Oh,
so therefore I'm hijacking this talk from now on. You've been warned. Ahora sí. Given that my talk is regarding methods of combination of significances and meta-analysis, I'm going to start with a brief reminder of certain elements of statistics. My apologies if this is something you're well versed, but given a set of probability measures on a common space omega endowed with a sigma algebra F, and a subset of these probability measures which we hypothesize that generate some sort of data, the power function of the test, contrasting our null hypothesis with some alternative that the data generating measure is in some subset in the complement of P0 with rejection region R, and decision statistic or test statistic X is the function that grabs a probability measure, not necessarily in the null hypothesis, and calculates the probability of rejection under that measure. So the probability of rejecting if the correct measure, the data generating measure, had been P. The size of this test is defined as the maximum type 1 error, the maximum false positive that one can expect by performing this decision, by using this decision rule, the maximum power under the null hypothesis that the probability, the data generating probability measure is in the null hypothesis set. So with a little bit of an abuse of notation, denoting by R sub alpha, the rejection region associated to size alpha. The p-value of the test is the random variable that, for an observation, x of omega, returns the smallest size for which the test would have rejected that observation. So the smallest threshold under which, for that observation, we would have fallen into the rejection category for a decision rule with size alpha. Under continuity of the observed statistic, when the decision statistic X is continuous, it holds that under the null hypothesis, the p-value has the uniform distribution on 0, 1. The probability of having observed something as extreme as what we observed generated by that same probability distribution is a random number between 0 and 1, which allows for several mathematical formulations that are straightforward and nice and yield not one but several combination statistic methods, all of them based on the probability integral transform. Namely, if we have an increasing CDF, the CDF of an absolutely continuous something with Lebesgue density, something invertible, so that its quantile function is exists. It's actually a function. This defines a function. This follows the distribution G. So the p-value under the null hypothesis can be pushed forward into essentially any distribution. I'll return in a moment to what do we do with this, but we're now considering the scenario. What motivates our development is the scenario in which we want to combine the information provided by multiple experiments on the same under the same scientific umbrella, if you will, something regarding the same parameters, something regarding the same scientific global hypothesis. Namely, if we want to study genetic association of a mutation, and in order to do that, we're going to combine the results of several clinical trials, several genomic-wide association studies, or if we're going to read 20 different papers regarding the same experiment performed under 20 different settings, we're going to have multiple results, multiple decisions, multiple significances. The significances, well, the word significance means p-value, different significances for different experiments, and we want to derive one common significance for the global null hypothesis. I'll make this example. Say
the last one. No. The next.
Say that again.
That.
Oh, yeah. So this line essentially says we're looking to combine the p-values, the information provided by all this scientific studies. That's not the only approach. There's the mean p that and several other approaches that look at only the order statistics of the p-values, but we're looking to pull and combine all of the information provided by all of the scientific studies.
So you will introduce in all the, for instance, in the studies, in the literature or the journal of biometric, and you will make a study like that.
Yeah, I'll grab multiple copies of like journals in biometric, statistics in medicine, biometrics, etc. And say like multiple researchers said we reject under this hypothesis. Some people said no. What do I do with that information? How do I derive one conclusion based on sometimes contradictory conclusions? How do I merge all that information? The basic example say, suppose you're tasking your students with constructing confidence intervals and testing the null hypothesis that the scale parameter of a distribution is 0. Student A at alpha equal 0.05 barely rejects the hypothesis, so his or her p-value would have been like something slightly smaller than 0.05. For student B, the p-value would have been something slightly higher, so the decision would have been different. C and D would have seen no evidence and would have had no reason to reject. F would have had stronger reason to reject. And say if this were normally distributed data and you had everyone's sample sizes and everyone's observed variances, you could construct your own confidence interval, combining all the data. But if people report only their p-value, you're tasked with this decision based on all of their decisions. How do you proceed? What's your final decision? What's the final global significance? Mathematically, we're going to consider without loss of generality, this is general enough. A left-sided p-value, a right-sided p-value would follow the same logic based on the fact that 1 minus uniform is also uniform. A sided p-value follows the same logic. This is general enough, trust me. A sequence of IID p-values spanning from different experiments, p-values being the CDF evaluated at the minimum sufficient observation statistic, each of them for the hypothesis that the observation statistic on the J study comes from CDF-F. And I did say something correct. They do not have to be IID. The F's, the p-values will be uniform, but the IID could correspond to different distributions. Say if we're doing clinical trials and 5 people show up to mine and 100 people show up to Avelio's, the propensity sizes will be binomial with different size parameters, but that is okay. So we have this and IID random variables under continuity, and we want to find a single type 1 error associated with the global null that all of our hypotheses were correct, that some medication is safe to use in my clinical trials, his, etc. Back to the probability integral transform. Recall that for any strictly increasing CDF, for any CDF of a continuous random variable, it's the push forward of a p-value that's uniformly distributed follows that CDFG. So you can push it to any continuous distribution, and in particular, you can push the p-value towards a continuous distribution in a family that's closed under convolution. Like the chi-square, not so much the logistic, but the logistic is fairly similar to the normal distribution for large scale parameters, so that in practice, it behaves more or less okay. The normal distribution, which is closed under infinite convolution, the Irwin-Hall distribution, which is the distribution of the sum of IID uniforms. And you can define a combination statistic analogous. Since they all have tractable distributions or good enough approximations, all of these ways of combining p-values yield a significance level based on comparing the observed value of the combination statistic with the quantile of its exact distribution under the null. So say a Fisher statistic that's too large means that there are a lot of very small p-values yielding this distribution not an adequate fit. Pearson is sensitive to p-values that are close to 0, etc. All of them under the null hypothesis have an exact distribution, and based on their quantiles, one can make a decision with exact significance. So in the continuous setting, how do you choose between the method that you're going to combine? They're all sensitive to different things. The mathematical answer and the practitioner's answer differ quite a while.
So I'm going to ask a really, really basic question because my...
Go ahead.
Okay, so your null hypothesis here, is it that your variable comes from a possible subset of measures, or you are fixing which measure it comes from?
In the example and without the loss of generality, I'm assuming that they come from a single distribution, but you can assume that they come from a countable set as long as the likelihood ratio is increasing in some way.
Okay, okay, so you need something for the inverse, I mean, for the p-value to be uniform.
Yeah, under the null hypothesis, the p-value will be uniform if that supremum is at an extreme of the null hypothesis set,
okay,
which is a mild enough hypothesis in statistic that is a sufficient condition for that is monotone likelihood ratio. That's something that most known distributions easily achieve in the parametric setting. But yeah, this is general enough, but it's not necessarily that I'm assuming one single fixed distribution, possibly assuming a boundary scenario in a family with monotone likelihood ratio.
Thank you.
Thank you for the question. Back to what I was saying, different methodologies of combining things that would be uniform were all of my null hypothesis correct, would still yield to a very different, very different statistics. This figure is from Rubin and Delancey from a comparison between continuous p-values paper in 2018. And here one can see that Fisher's statistic is very sensitive to a p-value of 0. Regardless of the value of the other p-value, a 0 leads to immediate rejection. And this is because logarithm of 0 pushes the whole thing to infinity. Pearson, on the other hand, is Fisher is skeptical. Pearson is a believer in the sense that somebody says this is highly likely, it tends to stay with that somebody and trust the result, not reject the meta-analysis as a whole. George's, which is an average of the two, is somewhat of a compromise. It resembles Stouffer's method based on the known resemblance between the logistic and the normal distribution for large N. And the Edgington method is the easiest one to explain to practitioners, although the Irwin-Hall distribution is not really easy to obtain in practice for large N, but for N equal to 2, here note that 1, 0, and 0, 1 yield to a combined p-value of 1/2. So it's very intuitive.
So just one question, how do you put in this method the fact that some studies have more people than the other? Like, is it
Regardless of the CDF of the p-value in the continuous case, regardless of what the CDF is, your p-value under the null is uniform.
yes, but
So-
somehow still it feels like if you have just one person, you are weighting it the same as if you have 1,000 people in the others.
Well, that is a practitioner's consideration, and you can say somebody performed a meta-analysis of a study with 2 people involved, and somebody performed a meta-analysis with a study of multiple people involved. You can choose something that's robust to weights. The normal distribution is closed under a scalar combination. That's Kramer's theorem. Or you can be skeptical and choose something that's very sensitive to the smallest p-value. So from a practitioner standpoint, there's no unique answer on how do you approach that. However, our motivation, one of my colleagues works at the Broad Institute, and they do cancer research with data that's very sensitive and censored, and it can be traced back. So confidentiality is important. So in general, our methodology is developed for the case where you know nothing but the p-value. Because in this settings, you know very little extra aside from that. Amitai, how am I doing on time? Or
You have 16 minutes, so you have like 35 minutes.
35? Good enough. Thank you. The mathematical answer is that, as Rubin and Delancey showed in 2018, most of this or combinations of them correspond to a likelihood ratio when the alternative hypothesis is parametric. So say the alternative hypothesis is that the p-value span from normal quantiles, Stouffer's optimal for the beta distribution that stochastically dominates the uniform distribution. A combination of Fisher and Pearson is optimal. Mathematically, like optimal in the sense of being UMP. I'm going to get to that later on, but the mathematical answer and the practitioner's answer is different. Nevertheless, it is an important consideration, as Avelio's question highlighted. Which method do you choose for combining p-values? However, the distributional theory is all straightforward. Not so much so in the discrete case. When your p-values come from
Excuse me, you don't have, because in a study, in probability and statistic, it is to how many times you can have some theoretical result where you bound, for instance, for some n fixed n, you can bound the distance between distributions, things like that. And there are some constants such that this distance is more than the other distance, things like that.
Yeah.
Here also.
Some concentration inequalities. We're going to provide something like this.
Yes.
And you're looking for concentration inequalities in which sense? You're looking for your combination method to be close to a distribution. In the continuous case, you don't need that because under the null hypothesis, the distribution are exact and known. In the discrete case, that's exactly what we're going to do. We're going to look for something that approximates well enough. Why would we need to do that in the discrete setting? It's because in the discrete setting, the CDF evaluated at a random variable that I believe, I hypothesize generates this X data. It's no longer a uniform random variable. It's no longer a discrete uniform anymore. It's not anymore a unique thing. Think about this. The cumulative distribution function of a binomial with parameters 7 and theta has 8 jumps, whereas 6 and theta has 7 jumps. So if we're back to the comparison of case control studies or clinical trials, if I have a smaller group size, my zero is stochastically bounded below by the zero of somebody with a larger group. So they're naturally going to obtain a lower p-value. So the p-values are no longer IID uniform, and they're no longer IID anything. Their shape may vary, and it's not a uniquely characterizable thing. So there's no hope for having a closed null distribution that's one size fits all, like in the continuous case. But the goal is still the same. We want to combine this significances provided by different practitioners into a single type 1 error for the global null.
May I ask you another stupid question?
Go
So
ahead.
because you don't know about the people, what happens if like two studies work with the same people, so you are not independent anymore? Can you somehow say something about it?
Correlated p-values pose a larger problem than the scope of my talk. Even in the continuous case, think about this: you're tasked to perform a meta-analysis, but it's close to midnight, and you have to submit your paper for the special issue. So you just repeat one p-value n times. That's not a. If you're performing Fisher, that's not a chi-square with 2n degrees of freedom. That's a chi-square with 2 degrees of freedom multiplied by n. So its variance explodes. That's dependent p-values are something way harder to trace, even though they show up a lot in genetic wide association studies, etc. We're gonna assume IID for the time being. And we're looking for combination methods that resemble continuity in when the distribution of the p-value is something that you look at and you say, well, this is discrete. They're usually like a staircase graph with jumps. But if it has a 1,000 jumps in the 0-1 interval, you would look at that and say, well, this is close enough to continuous under some metric. So back to Sedovit's question. The mathematical setting, which we're going to formulate for a discrete CDF, for a discrete p-value, a discrete left p-value. We're going to enumerate the values in its support by F1, F2, etc., arbitrarily casting F0 of 0, and if need be, F infinity at 1 if we're testing Poisson count data, something that doesn't really achieve 1. So we're looking for a random variable that retains the probability structure of X. So in between the quantiles given by the probability of X being less than or equal to something and X being strictly less than that same something, pushed back into the distribution of Y. In those quantiles, I want to define my observed statistic as one thing in a way that that distribution is as close as possible to the distribution of Y. And particularly when like I said, the staircase graph looks like something that's continuous enough. And in order to define close enough, we need to provide a measure of closeness, something that works well between discrete continuous pairs and something that reflects the geometry of the random variable and not only characterizes moments or something like that. The Wasserstein metric is going to be the choice of metric. The Wasserstein metric is the Euclidean distance between two random variables in an Euclidean space. So they're the expected value of the distance under the best possible copula generating that expected value. So when people too were looking for the best possible correlation structure between X and Y, they're going to be separate. In particular, when we have random variables, not random vectors or random anything more complicated, the Wasserstein metric between two probability measures has this closed form that's not no longer an infimum to the power p, which is the integral of the difference between the quantiles of f and g. So that tackles the other issue. The first issue was that it was well defined between a discrete continuous pair when one requires something to be absolutely continuous with respect to something else, to have a redundant negative derivative, like in the KL divergence. Those distances are not even well defined. And even distances that are like total variation, they put a gap of 1 between something that's supported on an accountable set and something that has a Lebesgue density. And that constant gap doesn't really allow us to quantify closeness. The Wasserstein metric, on the other hand, integrates the difference of quantiles across the entirety of the distributions of f and g. So we're looking for a minimizer of possible discrete CDF with respect to a continuous fixed CDF G. In order to obtain that, we appeal to, before that, graphically, this is what we do. Say In the leftmost panel, we have a smooth curve, which is the quantile function of the chi-square with 2 degrees of freedom, which is also the smooth curve that you see in the red panel. And here we have -2 log p for a discrete uniform, a partition of 4. So it has 4 jumps in its probability mass function, and we want to move the allocation of those jumps so that the shaded area corresponding to the difference between the quantiles is as little as mathematically possible. So that's
or the size of the jumps.
The integral of the difference between the size of the jumps is somewhat prescribed. You still want C equal to Ci to happen with the same probability as observation statistic X is equal to Xi. So the size of the jumps is somewhat prescribed. You just want to reallocate where they happen. But this is the quantile distribution, so you're looking at jumps in probability rather than jumps in value in the support. You see that on the y-axis. In order to find that minimizer, we appeal to the theorem of Cañas and Rosasco that, in short, tells us that if we have an arbitrary closed set, a subset of R, and we have a probability measure on the Borel-Sigma algebra of R, the closest measure to this arbitrary measure supported in this closed set, it is pushed forward. So the measure of the projection of a set onto the closed set S. No other measure for any order of the Wasserstein distance. No other measure is as close to rho as its projection onto a closed set S is. Looking at this in reverse, we have prescribed G. We have some discrete probability in a closed set that support varies. The optimal choice of the points of the support are the conditional expectations of the random variable with CDF G on each of the quantiles of the discrete statistics. This G-1 projects the quantile between inequality and strict inequality to the distribution of Y, and in those quantiles, we look for the conditional average of Y. So that's going to be the closest distribution to G. It's essentially the integral of the quantile function between the quantiles divided by the probability of that observation. In particular, being a conditional expectation, my optimizer shares the same first moment with the variable that it seeks to approximate. These are for the methods I described at the beginning. This would be the modifications when the discrete p-value takes the value fi, the ith largest value in the support of the discrete p-values. Fortunately, it shares the first moment, the approximation and the variable that we're aiming to approximate. But unfortunately, the second moment, the variance in particular, is larger than the variance of the discrete statistic, which from a mathematical viewpoint makes a lot of sense because we're collapsing all the distribution in an interval into a single point. So the variability is reduced according to the law of total variance. One can quantify how much is reduced. So the further apart that they are in Wasserstein distance, the further reduced that the variance is going to be, and that's not something one has control of beforehand. And this is a particularly bad issue because that reduction of variance sharing the first moment doesn't allow for critical comparison. When one looks at rejection decision, one looks for rejection so that if the null hypothesis is true, I don't make I don't commit an error rejecting a correct null hypothesis more than alpha times. This is a Fisher's combination statistic with variance, and this is the histogram corresponds to its discrete approximation with variance 2.52 as opposed to times n. with n equal 1,000 p-values, as opposed to the chi-square with 2,000 degrees of freedom, which has a relatively larger variance. So if we compare with a high quantile of that chi-square distribution, empirically, this is 1 million simulations. Empirically, we don't find anything above 2,200, something that can still happen with alpha equal to something of the order of 10 to the minus 4, something with 0.0001. So we're producing a significant bias. And I only illustrated Fisher because that's the one that we have well studied the most. That's the initial object of our study, but Pearson would be looking at the other tail of the distribution, and the reduced variance also causes that effect on the other side. Observed counts on a quantile happen with a relative frequency that's way less than the quantile of the distribution that we're looking to approximate. So we're if we follow this approach blindly, approximate and then test with the continuous distribution, we're going to be producing a highly conservative decision, and one that gets worse and worse as n gets larger, not better. The chi-square of 2n degrees of freedom has variance 4n, and this is going to be something strictly less than 4 multiplied by n. So the quantiles are going to be further and further apart in a way that you're not going to see something meaningful in the limit. So that needs correction, and the most naive approach is to replace the proxy approximating distribution, the distribution in the would-be continuous scenario that we're acknowledging has larger variance than the actual distribution of our statistic, with some other distribution in a location scale family that contains the null distribution under the continuous setting, that has the same first moment as my calibrated statistic, and also the same second moment as my calibrated statistic. This replacing the distribution of y with a distribution that matches the first two moments is essentially all that we need for asymptotic consistency. Namely, if we change the distribution of y for a distribution of y tilde n that matches the first two moments and is in an location scale family that also contains y, the probability that the empirical quantile of the combination statistic is below the p quantile of the approximation matching the first two moments is asymptotically b. This is nothing more than a consequence of a Lindenberg-Fellows central limit theorem, and it actually, and therefore it allows for generalization for something verifying the Lyapunov condition, which in the p-value context is that your experiments do not converge to a sequence that accumulates in something deterministic. You're not performing an experiment that always fails or always succeeds. With that, you have a bound on the third moment of the distribution of p, and Lyapunov's condition is met. So any combination statistic, and in particular the combination statistics that we propose with their new proxy distribution. So we're switching the chi-square for a gamma with fixed location parameter. The normal distribution, which is an approximation to the Irwin-Hall, a good enough approximation to the Irwin-Hall distribution. Actually, if you go to the Wikipedia page of the Irwin-Hall distribution, there's a graph that shows that under 4 iterations of addition of uniform distributions, you get something that's close enough to an exponential of minus x squared bound. So using this proxy distribution, we obtain asymptotic consistency in the sense that when we add in a large amount of p-values, the desired significance level is approximated by the empirical significance level. The simulations are adding 0, 100, 250, 500, and 1000 p-values. As we increase the number of p-values, the proportion of rejected combination tests approximate well their the prescribed type 1 error control at type 1 error equal 10%, 5%, and 1%. So thus far, the flavor of what we've introduced, modifications of something discrete to resemble something continuous to the best extent that it has one problem that's easily solved by moment matching, and that produces a consistent test under very general hypothesis. So the question remains.
Yeah, so I have the question remains.
How do you choose?
So I'm
Is
going
that
to
your
do
question?
my first year questions like my student. So what I missed was essentially you are trying to guess what is the best normal that approximates when you do the best normal that approximates, or you are adding another normal,
No,
so you're sorting out.
I'm not guessing, I'm just choosing the location and scale parameter of the normal so that they match the location, so that the moments of order 1 and 2 of the distribution of the sum statistics are matched.
And you do that, I mean, just empirically, you check what is the variance here, and then you.
I mean, under your null hypothesis that your p-value has a prescribed distribution, you can calculate the variance of that. It's a discrete random variable that goes between 0 and 1. So their mean and variance
So
are not
in your
something
null
particular.
hypothesis, you also know how many possible, I mean, how many jumps there are. Okay.
How many jumps there are and what are their sizes under the null.
This is
So
what I didn't get.
I'm performing some sort of clinical trial. I don't know the probability parameter, but my null hypothesis is that this effect is rare enough that it happens to less than 1% of the population. You know that theta, so you know the magnitude of the jumps as well. So these variance is not hard to calculate, and neither is the mean, as the mean matched the mean of the quantity that you wanted to produce.
So you assume that the p-values were IID, but in this case, what you have like different jumps may amount to the amount of people you have, or like the amount of mods you have checked now.
Yeah, no, I'm assuming for the purpose of this combination strategy that the p-values are IID, but the main result, in the main result, you can replace IID by a sequence of p-values whose this null distribution verifies the Lindenberg-Feller condition. And in that case, you have to match the mean and variance of the sum of statistics that don't really have the same mean or the same variance, but their variance are nevertheless calculated. So if you're performing meta-analysis and 10 p-values come from here, 10 p-values come from there, your mean and variance are going to be 10 times this plus 10 times that, and 100 times this plus 100 times that. So it's a procedure that mathematically poses no additional burden.
Thank you.
Make sense?
Yes.
Okay, so the question remains, not that question, the question remains. Once we've shown asymptotic consistence under very mild hypothesis, and we've empirically verified it for our approximation of the 5 statistics of various type 1 error control levels, which one do you choose? How am I doing on time, everything?
You have 15-20 minutes.
15-20 minutes, more than enough. So I gave you once a general recipe to build your combination statistic, and following that recipe, you can build your Fisher analog, your Stouffer analog, you can build analogs for all the combination statistics presented. So which one do you choose under your setting? And the mathematical answer would be the uniformly most powerful, the uniformly most powerful test resulting by the quantile of that combination statistic. Why is a uniformly most powerful test? A test that has an upper bound on the power function uniformly, mathematically speaking. Intuitively speaking, is that if we want to sacrifice, I mean, if we want to gain type 1 error control, recall that type 1 error was the highest probability of incorrect rejection with our test. So if there's another test that has smaller than or equal type 1 error than our test with rejection region R alpha, then for any probability in the alternative region, then the probability of rejecting will be smaller than the probability of rejecting with our original test. So gain here comes at a cost in sacrificing power under the alternative. That's and the for all yields a uniform most power. What is the uniformly most powerful test? The likelihood ratio test. I don't know if you recall this, the Corlin-Rubin theorem. You may not recall this flavor, but you probably do recall the Neyman Pearson lemma. The Corlin-Rubin, assuming that you have a parametric family under a usual hypothesis that there's a sigma finite measure that dominates the entire thing, just for the purpose that the likelihood ratio exists. And if that likelihood ratio exists, and it's non-decreasing once you move the parametric identification upwards, then the test that rejects whenever the likelihood ratio is bigger than some constant that under the null has type 1 error alpha is the UMPU test. Make sense? So increasing likelihood ratio or any increasing function of the likelihood ratio will also be an increasing likelihood ratio. If you compose this L function with any monotone function, like logarithm, you will also obtain something that has monotone likelihood ratio and therefore will yield the uniformly most powerful test. So our tests, which are sums or logarithms of products, logarithms of IID distribution, will be likelihood ratios whenever the alternative is that the p-value is proportional to the exponential of the thank you, Anya, to the exponential of the numerator of the conditional expectation multiplied by what would be the same probability under the null. So depending on what you're contrasting with, if your alternative is that your p-value is proportional to this quantity, then you win with a combination statistic that's an approximation to this probability integral transform. So it might be one of the 5 I presented. It might be something entirely different. We have been able to prove that in most, that we have shown that, like I said, it depends on the shape of the alternative. We've been able to show that Fisher's optimal in the majority of the cases we have been thinking of, but so far we haven't gotten anything general enough for publication, so I'll give you a couple of examples. Detection of rare mutations. Assume that under the null your p-values are IID something discrete, and you have a sparse but strong alternative, meaning that suppose that your observation statistic come from counts from exponential geometric, something in a power series family, with null mean parameter lambda 0, and the alternative is that you generate p-values that are stochastically significantly smaller than the PIs in a very small proportion of cases. Under that specification of the alternative, Fisher's is the likelihood ratio that we're looking for. Here, what we did was we generated count data. We assumed that we're generating like hospitalization rates in 1,000 hospitals and combining the p-values associated to smaller rates, so higher means than what is in the null hypothesis. So think about a disease that strongly affects some very prescribed subset of the population, say like an outbreak of a viral disease in a rural location, so that a few hospitalization rates will be high enough, but the other ones will be indistinguishable from the general setting. In that case, we've shown that we show that Fisher's is UMPU, and in the simulation study, we see that Fisher bounds by a wide margin all of the other combination strategies, in particular Pearson, and this is due to what we discussed at the very beginning. Pearson is a believer, so if Pearson sees one hospital or a few hospitals with normal hospitalization rates, it's going to refrain from rejecting. So from From a practitioner point of view, this is intuitive but mathematically interesting nonetheless. Another, how am I doing on time?
Like 10, 15.
Oh, I have time for all of my examples. Great. I'm gonna be correct twice a day. No less.
I think it's never fun. Maybe twice a year when.
¿Cómo? Clever.
Que no mágico, está avanzando, pero creo, pero no está ahora.
Entonces, 0 times a year, or a ver, está avanzando.
Creo que está avanzando un poquitito más lento que lo que
Different rate.
Así que quizá un par de veces.
Somebody could perform a statistical analysis on that. Genetic association studies. I don't know if you're familiar with GWAS. You have a bunch of genes and you're looking for something associated with a specific disease, like this gene makes you more propense to cancer, this, or maybe something genetic makes us Chileans more propense to gallbladder stones, whatever it is. Usually the approach to that is linear regression on each of the disease markers, logistic regression more than linear regression, but a proxy of linear regression on the genetic markers on the disease status based on the genetic markers. And the usual test for linear regression is that a slope is equal to something equal to 0 in the horizontal case where you see no effect from your variable x in your outcome y. Since those residuals are normally distributed, Stouffer is UMP for that combination. This is a lie. It's weighted Stouffer, but Stouffer with weights that multiplied by positive quantities that add up to 1 yields a uniformly most powerful test. However, in practice, the power loss is not that. I mean, not in practice. In simulations, the power loss is not as large as in the Fisher case where we showed optimality, and in practice, it looks converting to power 1 much faster. Last example. Last example is Fisher's exact test. I don't know if you're familiar with this. You're gonna, if your first intuition is to tell me that this is a non-parametric test, give me 1 second. This is a typical association study between the presence of disease associated with an attribute. Having or not having a specific gene gives you diabetes, cancer, or something versus it doesn't. One has usually prescribed number of participants in the study, of cases, and of individuals with the attribute or the marker for that one speculates is correlated with the case. So filling out this table requires only 1 random variable, x, that under the null hypothesis of independence is hypergeometric. Essentially, I'm drawing balls from an urn. I'm drawing cable from an urn with this composition of balls, and I'm seeing how many of them are marked with C. So hypergeometric under the null. In the case where you have an association, well, it depends. Your alternative depends on the strength of that association. We frame that as a parametric test where the null hypothesis, I mean, the parameter is the conditional probability of association, P, probability that you have a disease given that you have certain market. The independent hypothesis is that the conditional probability is equal to the unconditional probability, therefore number of cases in the population or in the study. And what we did is that we generated binomial data with size number of attributes and probability P, with P ranging from 0 to 1 in a balanced study, assuming that this was 1/2. And under certain additional specifications of the distribution of on the number of cases in control, no additional specification of the distribution, that cases conditional attributes or binomial with parameter P, we obtained that Fisher was also UMP. And here I made a mistake of cutting the probability of association. Like I said, it was a balanced study, so 1/2 what's the optimal threshold. So please look only at this middle band, but with a left alternative that having an attribute reduces your propensity to the case. They all achieve power 1 super fast, but Fisher is faster than most others. And once again, Pearson has this issue that it tends to believe high p-values. So it tends to be a blind believer. We hypothesize that Fisher's combination is going to be UMP in most cases where your alternative hypothesis is an intersection. In order to observe something in an intersection, you only need to observe one case. The natural complement of an intersection is a union, but it's always leads to misconceptions. The the complement of an intersection is a union, but you can specify, like we did in the examples, a specific form of the alternative. And we believe that we haven't been able to prove this, not by a long shot, but we're still making progress towards that whenever the alternative is also an intersection, Fisher, based on the fact that it tends to believe in the continuous case and also in the discrete case, one rejection, one p-value that's small enough is going to be uniformly most powerful. We have been able to show that it's UMP in most cases of that flavor, like sparse signals. We're trying to combine weak and sparse signal with a with some sort of threshold on the sparsity parameter, but like I said, this is work in progress. I'll let you know when this is on archive, ideally with sufficient conditions under which Fisher statistic is optimal. For the time being, that's my talk. Thank you for your attention, and I'll open the floor for questions or comments.
Questions?
Comments, concerns, remarks? I guess I moved too far away from the probability topic for one session.
No, esto es común.
No, pero ya no había hartas preguntas.
Well, if not, then we.
Maybe somebody from the audience,
Yeah.
from the student audience.
Good.
Any raised hand there?
Yeah, from the Zoom.
Elector, can you look my?
Gonzalo,
I don't know.
Hi, Gonzalo. Do you hear me?
some method are more stable when to move your discrete.
In empirically, this is not something that we've studied theoretically, but empirically, Fisher and Pearson, and particularly with Fisher, tend to be more unstable. They tend to be less robust to not null hypothesis violation, but general constraint violations. If you specify that something is binomial with size 10 and it was actually Poisson and you move to 11, if you use Poisson to simulate binomial with high counts, Fisher can be a little bit iffy. Yeah, and empirically we have that. Theoretically, we haven't done a study of that. We're still trying to figure out what is UMPU, so we haven't looked at asymptotic stability or stability questions. Raul?
When you combine these p-values, you're pooling information, that's right.
Yes.
And then do you take into account the size of the samples that were used in the studies? Because you only get a p-value, but that may come from, I don't know, huge data sets, and another may be just some small.
Yeah, I understand that.
There's a kind of, weighing these p-values and samples, depending on the sample sizes.
You can do that in the discrete case and in the continuous case, particularly with the constraint that you want to some extent retain the null hypothesis distribution of the combiner. However, the methodology that we developed was based on having no further information than the p-value. So anything about a group size or effect size is lost or censored before the analysis. But in the case where it's not, or in the case where that's partial, where you're studying like some rare disease that you want to know how many people have it, but you don't want to tell the researcher who has it, you can report sample sizes, and in that case, Stouffer is more adequate as it retains the normal distribution. It's more adequate to put weights inverse to n to the -1/2. You can do that with Fisher. Actually, there's a recent work from one of my colleagues on the G Fisher that projects back to quantiles of a gamma that incorporates a weight, because a weighted gamma is a gamma with a different scale parameter. The gamma distribution passes the weight onto one parameter specifically, so you can combine.
Anyway, in practice, I would be reluctant to use information, p-values coming from a very limited study like 10, size 10 compared to another one with several hundred.
Sometimes that's
Well, that's
all you have. Sometimes that,
Maybe
yeah.
it's strange that you find a study where nobody reports the size of data set used.
Yeah, so, and
Clear, I mean,
in some cases, yeah, in most scientific studies and most published peer-reviewed work.
to begin with.
Yeah.
That journal.
I mean, if you're getting data from a hospital, they're not going to give you anything
Oh,
but
right.
the p-value. Yeah, I know that it's a weird case, and I should have elaborated more on my initial constraints. One of my colleagues is appointed by the Broad Institute for Cancer Research, and that people like to work under the scenario where as little as possible is known, because that's often reality.
And a small thing, what happens if you have the same null hypothesis, but everyone has a different adversarial one? Can you?
Well, then your global alternative is going to have to combine that in some way. So say some example of that could be that the distribution of something has the same scale parameter for everyone versus that it's higher for men and smaller for women, or higher for group A and smaller for group B. You're going to have to prescribe that as H alternative. F stochastically dominates in this scenario to a true distribution and is stochastically dominated above in this other scenario. Specification of the alternative is key in finding what is the uniformly most powerful decision statistic for your purpose.
Is there any Bayesian approach?
No, because with respect to the question of Raul,
Yes.
I think that the Bayesian approach will be better instead of because when you see a study,
Yeah, like
if they
very
come
big-
from an hospital, the hospital generalizes some sense with respect to information.
From a mathematical point of view, yes, like you would you would be able to combine better using a Bayesian approach, but randomizing a decision. And I know Bayesian analysis is not randomizing, but practitioners in particular in the biological fields are very averse to introducing any extra measure of randomness that it's not the result of the actual observed statistics. So getting them to change the observation X or G-1 of X to C, as we're doing, that's been a very cumbersome wall to pass. So introducing a Bayesian framework for decision and asking the practitioner to incorporate a prior, even if it's a generic prior, like
it's given by the journal, or given by the journal where you publish what the study is, or where the hospital has come from, or where the group of people that they have made. Or...
Yeah, if you do this by and for mathematicians, it may be a Bayesian approach could help. That's a very good suggestion, actually. I'll look into that. But in the sense of like driving this to presenting this to workflow applications, people are gonna like abstain from
No, no.
Bayesian analysis. I'm sure this is something you've encountered a couple of times too.
Good, very good.
Yes. Any more questions? If not, then we thank Gonzalo again.
Gracias. Y gracias.